guys, we're ready for the next session. Guys, you ready?
Yeah, sure.
Okay,
So, may I first ask, have any of you ever used COMSOL before?
No.
None of you? And okay, only one.
I have
Of course,
Great.
yeah. But now the question is, have you all get it on your computer?
No, I need to, but I think I need some license.
License?
Yeah.
Okay, so I mean, because this time we don't have this workshop licenses, so I think if you later want to do practices, maybe the best way is you kind of you can ask your colleagues or someone who have already received the trial licenses. I think this one is not the trial licenses they gave is not locked to a single computer, but you can kind of use it on multiple ones. So maybe you can just maybe borrow another colleague that may got the license already. Yeah, or otherwise, I mean, it's all fine, or you just watched him. I mean, when you are setting up the model. So yeah, or in the worst case, we can try if we can still use EPFL licenses. But the EPFL's license will, I said, only we have 10 slots, and usually pretty occupied. So yeah, just you have to try a lot. Yeah, but later that's a problem for the exercise session. So now I'm just going to briefly introduce how to solve waveguide modes using COMSOL. Yeah, this is the first part of the COMSOL series sessions, and in the afternoon. Later after me, there will be another session given by my colleagues that goes to a bit more detail on how to estimate band loss for the band waveguides. And yeah, so first I'm going to introduce a bit of the principle. So basically what we are solving for. So I mean, our starting point is basically the wave equation in dielectrics. So most of us, I think, also most of you are also working with dielectrics, kind of embedded in another kind of dielectrics. So rather than what's more common on electrodynamics textbooks that are metal enclosed microwave waveguides. So basically, we are solving this wave equation where you have actually everything described by the refractive index. And here, also for simplicity, we are mostly considering that the cases that we have a uniform refractive index across the materials. So kind of the space is piecewise uniform in terms of what consists it. And in this case, you can write a wave equation, and of course you can put kind of a boundary condition to that is defined by the materials. And then later in kind of mathematics, we can do a separation of variable. Basically, we put we don't want to solve the wave propagation in 3D, but to simplify the problem, we can try to reduce this problem into 2D to kind of solve for mode field. And basically, we can imagine that in the 3D space, how the wave field is basically the mode field times the propagation constant. So we can do kind of this separation of variable, like how you started in you learned in mathematics physics. And basically, you can write the electric field be like this. I mean, EXYZ to have one component that is only dependent on the EXY, which here is basically the cross section of the waveguide, and also another exponential factor that is only only dependent on the Z direction, which is along the waveguide basically. And then you can kind of reduce the equation to just separate this out, separate this exponential factor out, and kind of reduce the problem into our eigenvalue problem of this kind of Helmholtz equation. It's now Helmholtz equation, and I mean, if you are less familiar, you can refer to mathematics, physics textbooks, and also maybe also on Wikipedia. So yeah, you can also do the same for magnetic field, but it will be a very similar formula, and because of usually dielectrics, you describe them with with a variable epsilon, which is variable, dielectric constant, and your the permittivity is almost always 1. So yeah, everything I think okay, it will be more relevant to write the thing in electric field because of smaller things that depends on the refractive index directly. And now the solving for the electric field along the waveguide becomes first solving a 2D eigenvalue problem, and okay, considering its propagation along the waveguide by just times this exponential factor. Yeah, so just note that here, most of the cases that we are doing problems that is a bit different than what you find in electrodynamics books. So yeah, because they usually consider metal enclosed waveguides, and they kind of have their results. For example, if you find in textbooks, then you know that it doesn't exist since like TM T00 mode, TM00 mode. But here for dielectric waveguides, yeah, there is this T00 mode, TM00 mode. It kind of also defined slightly differently. Yeah, also just to introduce you to kind of some different kinds of waveguides you usually encounter. So maybe, yeah, if you have a dielectric coated with higher index as a waveguide core, you coat it on kind of another low index thing, and then okay, you form the so-called slab waveguide. And in many cases that you also kind of do some lithography to define a structure on the higher index material. Then you form either this kind of buried waveguides, and also if you do it differently by ion exchange, you can have some shape like this diffused waveguide. And also, yeah, basically just it carries all different names that describes slightly different geometries. And when, for example, when you are doing this definition by etching the waveguide, but don't overcoat it with a low index material, then you have this ridge waveguide. And if you don't etch through, you get rib waveguides. Okay, just different people do slightly different things. But the geometry is basically just like this. So yeah, and most of the case, due to also limitation in fabrication process, is also piecewise. The refractive index is piecewise linear. So. But also just to mention, when we set up the problem, you can also have refractive index that is dependent on the geometry. So if you somehow can manage to fabricate this thing, you certainly can simulate it in COMSOL as well. Just when you're defining a material, you need to play some tricks. So yeah. So here, just to say how this is how we usually call our modes. So yeah, basically this thing we call is T00 mode. Basically, you have only a single bump of electric field that is concentrated along kind of your geometric center of your high index waveguide core. And this, and also when the majority of the electric field is on the horizontal plane, and in this case we call it T mode, TE mode. And okay, if it's kind of only a single bump, then we call it the T00 mode, fundamental TE mode. And also for there also exists higher order modes, like, for example, in some cases, you can form a mode that with 2 bumps or 3 bumps. Yeah, it kind of depends on what geometry of the waveguide you have. So, okay, you can kind of think about it kind of instinctively, that if you have wider waveguide, or then you can kind of support more possible modes. Like, if, for example, also just to put it in kind of perspective, if you have a silicon nitride waveguide buried in silicon oxide, then if you have it, have the silicon nitride to be something like 800 nanometers thick, That is something that you can typically find in foundries. Yeah. Then if you put the the waveguide width to be very narrow. For example, yeah, you see here in this figure that is less than less than 0.7-ish micron wide. Then in this case, you are only having the fundamental T and TM modes. So this we call single mode waveguides. And also if we make it wider, you are beginning to see there the waveguide can support more than one mode. Yeah. So also, of course, this also applies for this so-called TM mode. TM mode means the magnetic field is along the horizontal plane. It's in the horizontal plane. Yeah. Also, yeah, you sometimes exist as higher order modes. So yeah, in this case, of course, you know that if the wave is kind of propagating along the waveguide, so its pointing vector is along the waveguide, then your kind of electric field, I would say kind of average distance, the electric field is kind of horizontal to the magnetic field. So yeah, if you have a TE mode, then you can kind of imagine most of the magnetic field is oscillating, vertical to the horizontal plane. Yeah. Yeah, and also for our convenience, now we kind of define this two parameters. Just effective index and the propagation constant to describe each of these modes. This basically is related to the eigenvalue we solved for this K0. But K0 has a inconvenient unit because it's kind of proportional to the inverse of the wavelengths, which is huge in kind of our common units. So yeah, we kind of do it differently. We describe this as a so-called effective index. So basically, this is a definition of the effective index. And you can just compare that if you have a uniform dielectric, and what will be the k kind of propagation constant? What will be the k and the beta in a uniform dielectric? Basically, you are replacing the NEFF in the formula here by that. The N of the uniform material. So yeah, and basically in this case, you can understand this effective index as a thing that's kind of average, a kind of weighted average of the materials refractive index that is filled by the mode field that is propagating along the waveguide. So yeah, and yeah, you should just consider if you have a bulk, you have a uniform material that you are not really confining the light, then so effective index is basically just the index of the material itself. Yeah, and also as a rule of thumb that it's not always true, but for most weakly confined modes that unless you really engineer some crazy structures, that's effective index of the mode is usually between the index of the waveguide core and the cladding. Yeah, of course there are exceptional cases, but if you just consider rectangular waveguide, then that's always true. And then it's a kind of good to know thing. Also, because later you will see when you're setting up a simulation model, many tools will require you to kind of supply a gas for your kind of your eigenvalue that allows the solver to kind of initiate the iteration process. So in this case, you can just supply a effective index gas that is between the highest refractive index among your waveguide cross section and also between your cladding. And there is another thing that you can play when you are modeling the modeling a cross section. Basically, this T and TM fundamental modes and higher order modes also have some symmetrical properties. So basically, for T modes, you find they have symmetries in the x = 0 line, and the TM modes have symmetries in the y = 0 lines. Yeah, sorry. Okay, for T and TM modes, they have symmetries in both these two lines, but it's kind of a slight, kind of different. So if it's T mode, then you have basically you have no tangential electric field. Sorry, you have no electric field that is kind of vertical to the horizontal plane. So all the electric field is parallel to the, I mean, horizontal plane at the point of x equals 0. And that, of course, only applies when you have a rectangular or, I mean, kind of, I mean, symmetrical shape of geometry. So yeah, this can somehow, by just using these conditions cleverly, and yeah, your geometry is right, you can kind of reduce the region that you need to solve by up to 1/4. Basically, just yeah, like this. If you consider the entire waveguide cross section, it will be like this. And if you know here, you have only an electric field that is yeah, in x direction, then basically you can basically cut this into 4, and you set here as a perfect electric conductor, yeah, boundary condition, basically by assuming that all the electric field can only be perpendicular to this, yeah, interface line. And also, yeah, we consider here, if it's TE mode, then the magnetic field can also be only vertical at the y equals 0 line. And you can then cut it also in here in half and set this to a perfect magnetic conductor. So that's also assumes that the force is solver to let the magnetic field to be perpendicular to the boundary. Yeah, and then okay, you basically can cut the problem into 4, and then kind of simplifies the simulation. Yeah, but of course, this only relevant when you have a fully symmetrical structure. Yes.
I don't understand what's the link between TV mode and the axis of symmetry, the electric conductor.
So okay, so I mean, when we kind of call it, well, so okay, this actually I have to admit it kind of lacks a bit of rigidity, but I think this holds for well, for homogeneous material that is not isotropic, which is mostly true for kind of amorphous materials that you're working with, like silicon nitride or silicon oxide or whatever. For these things, then you can prove that it kind of exists two kinds of mode that just have a distinguishing between T and TM. And okay, in this case, that for T mode that you really you basically kind of just have this symmetry of waveguides. Symmetry of the electric field. That if you cut it, cut it in half, it's the electric field in the minus half plane is kind of just folded back to the electric field in the positive half plane. So yeah, just you kind of get it. And also magnetic field also falls differently along the y equals 0 line to the bottom half plane and the upper half plane. Basically, for example, if you see the electric field here on the right, then okay, if it's pointing right at, for example, this point, and then I can see here in this point also it's also pointing in this direction. Yeah, you can. So also you can see here, I mean, I don't know if you guys can see it very clearly. Basically here, this arrow shows how the electric field are distributed in the T mode. And T00 and like this, or going in this way. And in E10, it goes this way. But all are parallel. Here, basically flows back. And at the zero plane, then you must have no perpendicular component, the vertical component. And also for TM mode is kind of the reverse. So basically the electric field is like this. After this.
Why you don't have a vertical component for TE mode? I thought TE means there is no electric field in the direction of propagation, but what you could also have.
So that's true. Yeah, I think that's for metallic waveguides. If you call TE, they have no electric field along the propagation direction. But here, it's a bit different. Yeah. Just define a different way.
When waveguides to call TE when the electric field is parallel to the waveguide.
Ah, okay.
And TM is when the electric field is perpendicular to the waveguide.
Okay.
That's just a convention for integrated component.
Yeah. Okay.
And that's a bit different from the microwave
Yeah.
mode.
And also, if you refer to fiber literature, they also have a very different kind of mode nomenclature. They call it just I mean, they just name it differently.
And actually, they're called quasi-TE and quasi-TM.
Yeah.
Because it's never truly horizontal, truly vertical, but just to distinguish them, we name them TE when it's mostly horizontal, and TM when it's mostly vertical.
Yeah, thanks for the explanation. And also, what I described is applying for kind of just straight waveguide. But in many cases, you also look into if you have a bent waveguide. For example, you are simulating a ring resonator, or you have a waveguide bent in your design. Then actually, there is a more or less simple way to also still reduce the problem into a 2D cross section, so that you don't need to run a fully 3D simulation. Which, of course, you can still do, and in many cases are necessary. Also they will be described in tomorrow's session with a full wave FDTD simulation. But here you can think about that how to simplify and kind of get a physical picture by just still doing the same reduction to 2D and so for cross section. Basically, here what's different is before we are doing the separation of variable in kind of rectangular coordinate system, but here we do it differently. We are instead doing this mathematics in cylindric coordinates. Basically, you have still the same wave equation, but write it kind of, write the Navier in different operator in coordinates. In cylindric coordinate system, and then you can still do the same separation of variable, but instead of separate for propagation constant along the z direction, but consider that separation of variable in the theta direction. Here. And then basically you can do the same. That also reduce the same problem, reduce the problem into 2D, but looking at cross section radially. And there is also another kind of way to understand this. It's kind of a bit more advanced, but you can think of, you can actually refer to the thing I linked here. It's a document I linked here by Jugend. But basically, you kind of you can consider that if you have a bent geometry, you can transform, do a kind of conformal mapping that maps the geometry that in the cylindrical coordinate into still in rectangular coordinate. But in this case, you will have to kind of modify your coordinate system by doing this mapping. And also here you will need to kind of modify your refractive index rather than kind of this piecewise linear description into kind of this tilted a tilted function. Basically, that's what's on the outer boundary. The experience is further away from the curvature center that experience a higher refractive index. They basically have a shape like this. So also, this can kind of enable you to think it more instinctively. That if you have waveguide bend, for example, here, considering a waveguide that is bending, bending this way. The wave is just like the picture, bending this way. Then you will see that waveguide mode is kind of squeezed out towards the way that is towards the direction away from the radius, center of radius. Also, there's a instinctive picture that you can also understand like this, because for example, here you do the conformal mapping, you will see that on the outer side of the waveguide, you effectively have a higher refractive index. You can also imagine like this. So if you plot the equal phase fronts here, basically, then because of the outer side of the waveguide is for the same amount of angle of rotation, you are likely to travel a bit longer. So the accumulated phase is also a bit more. Okay, then also this, if you experience more phase in kind of the same amount of distance or angle distance travel, this also kind of instinctively corresponds to our refractive index that is higher. So then you can just think like this. So what's this away from the radius of curvature have effectively higher index. So the most routinely gets squeezed out. And of course, if you are squeezing the mode a little bit too hard, you're bending the mode too hard, and so that here, you no longer have kind of a beautiful step like this, but basically you're bending it too hard, so that effective index at the very right edge of the geometry is too high that you can start to lose your light. So the mode is no longer confined, and this will be actually the main topic in the second session by my colleague Anna and Jihan. So also on COMSOL you can very straightforwardly setting up models in this kind of cylindric coordinates that you will also see later in the model that I think I shared for the exercise session. That you can basically define the model differently instead of in 2D, but to be 2D axis symmetric. Also later, then we need to one important parameter for our work in integrated photonics is the dispersion of the waveguides. You may know that materials, all the materials, bulk material, they have their own dispersion. Of course, due to also how the light wave is interacting with atomic systems. When this materials are fabricated into a waveguide, you kind of have a additional control or variability in what's the dispersion of the wave guided in the waveguides. So you have not only the material dispersion and also kind of a geometrical dispersion. The source of the geometric dispersion you can kind of also instinctively think it like this. So if you have dielectric that is that has higher index than the surrounding cladding, then you think that if you have your wavelength is shorter, is shorter, then in this case the light can be a bit more confined in the core of the waveguide. And in this case, that's the core's refractive index is higher than the outer side. In this case, if the wavelength is shorter, your light more confined, your effective index is also higher because your mode feels a bit more of the waveguide core instead of cladding. So this kind of gives you our additional geometrical dispersion. Also, just look at how you find how the dispersion is in silicon nitride. So basically here, this is I'll get to this bit later. But if you plot the refractive index versus the wavelengths for different kind of silicon nitrides, yeah, silicon nitride have different, all different, you find all different silicon nitride in your usual fabrication. This I also go to a bit later. And yeah, if you have different silicon nitride refractive index profiles, you will also see that it has a, okay, here we call it native dispersion parameter, a group velocity dispersion parameter. But after considering the waveguides effects, you can have either positive or negative dispersion by changing the geometry parameters. I mean, so just know that, okay, you can really, your waveguide dispersion is really depends on how it's designed, not only on the material itself. And also just to introduce a bit, it's also, okay, it's a problem that is, has been quite widespread. That is, you have many different definitions of the waveguide dispersion parameter. So yeah, for example, fiber, okay, as another kind of dielectric waveguide, they also have their own dispersion, profiles. And people working with fibers, they usually describe their dispersion as this kind of beta parameter. Basically, this beta parameter, how it's like is basically radial phase propagation constant. Yeah, that is this omega times an EPFL over C. And you can do a tidal expansion against the omega parameter centered at some center wavelength. And then you can write the parameters as beta 0, beta 1, beta 2. And in most of the cases, we are concerned about the beta 2, which is, they call this group velocity dispersion. Basically, yeah, okay. The beta 1 is basically the group velocity. I think most of you are familiar with. Basically, so yeah, you think about if you have wave packet centered at a wavelength, that is how fast the wave packet propagates. And yeah, also, and beta 2 means how the group velocity is changing against the center frequency of that wave packet. So yeah, in particular, also I think Shasha has described for nonlinear physics and for the kind of if you are considering soliton formation, yeah, this second order dispersion will be paramount importance. Yeah, and this is beta 2, and also there are people defining this group velocity dispersion parameter in a different way, and to make it more confusing for you, have a different sign. So yeah, basically you can define it differently. Yeah, instead of using the tidal extensions parameter, you can do it as d beta 1 d lambda. And okay, you can also write it in different forms, but just note here you have a minus sign in front of beta 2. And so that's, yeah, you just need to be very careful. So normal GVD means, normal GVD that, yeah, something that doesn't support, solitons, yeah, means that d less than 1 and beta, yeah, more than 0. Yeah, also just here in the plots I referred to is also that's d. Okay, so also kind of rule of thumb. If you are considering rectangular silicon nitride waveguides, yeah, basically if you have thicker silicon nitride, so the waveguide is more closer to rectangular in this way by having thicker silicon nitride layer, your dispersion your D parameter will get higher and higher. So here this is 0.75, 0.8, 0.75. So basically, the thicker silicon nitride you get is it means you have more anomalous, GVD. That's also, for example, why Logitech want to have two platforms like one thinner, one thicker. Yeah, thicker is 800 because that one kind of support soliton have anomalous GVD. And also looking at another dimension of your waveguide's width. If your waveguide width is wider, from 1.4 extend to 2.2. Basically, if you still look at the same wavelengths, you will see that the wider waveguides kind of tends to acquire a more normal GVD. So yeah, if you just should look at the combine here, you'll see basically yeah. So if you want to have a stronger normal GVD, then you will design a waveguide that is a bit I mean it's nano but a bit thick. Yeah. Yeah, later you will be able to reproduce this process rather simply. Yeah, with COMSOL, you can do it yourself and just be a bit. Okay, you will later know that okay, this plot will actually require quite some simulation. So because each of the points means that you need to solve the eigenvalue problem for some tens of times, and each point in this plot, yeah. And so the entire plot will be some kind of thousands of simulations. But yeah, I mean, later I show you that with the parameter sweep feature in COMSOL, or you can do it with your custom script, is also still, yeah, still quite manageable to do this. Also, I think, yeah, just getting a step closer to what Sasha has shown. For micro-resonators, we usually tend to use yet another nomenclature for the dispersion. We call it integrated dispersion. Basically, these are describing how far this resonance is in a resonator is okay apart from a regular grid. So yeah, first okay, easily you can write the condition of the resonator that it forms a resonance is the round trip phase of the the wave propagating the waveguide forming the waveguide resonator to be 2 pi times n is an integer, right? And then okay, for each of the integer you can name it okay, each integer m, then you can kind of write down what's the where you have actually this resonance. Yeah, this omega m, I mean, is like this. Basically, the round trip phase is 2 pi and times m. And then, okay, you can conversely solve for the omega. Yeah, where the resonance happened once you know that's how the effective index relates with frequency. Basically, the dispersion profile. Once you know that, then you can compute where the resonances are. And you can check that how far they are apart from the from a regular grid that has a separation of they call FSR, finite spectral range. And then okay, you can also do the same Taylor expansion. I mean, yeah, getting it gets to this kind of D2 and D3 parameters. And here the mu is basically the index of the mode. Yeah. Compared to our center mode that you just select arbitrarily. Okay, then you can write the extension, you get a D1, and yeah. It's actually, oh yeah, then you can write this, you write the D2, write the D3. And okay, if you are you have simulated the beta parameters for the waveguide dispersion. Sometimes you can also use this simplified equation that's kind of as an extension, kind of just directly arrive to the D2. If you have beta 2, you can compute the D2, and also maybe also for D3, but the equations are a bit more complicated. So yeah, so you can also see that okay, D2 has also a minus sign compared to beta 2. So if beta 2 is larger than 0, this means the D is less than 0. So it's kind of have the same sign as the D, this group velocity dispersion parameter here. It has the same sign of the D. So it means that if you have D2 that is larger than 0, then you have anomalous dispersion. Yeah, and also just to say that here also you can derive the once you know the dispersion profile, another very important parameter you need to find out most of the cases also the group index, the NG, which is also directly related to, the group velocity, and also it's just simply the beta 1, 1 over beta 1, and this. Okay, when we are working with micro-resonators, this NG also have a very important reason to know. It also just relates to the optical loss that of the light propagating along the waveguide versus what's a resonator line width. Yeah, basically the formula here. So yeah, I think that's all that I have for the theoretical part. Then I can kind of quickly jump to the how you really create the model in COMSOL and to simulate the waveguide dispersion and how the mode will look like or your actual waveguide. So I think I should have already sent you a starting model, but I still want to kind of briefly show through some screenshots that okay how you some common problem that or how some ideas that how we do it. So yeah, when you are creating a model, you can just follow the setup visa. But here there will be two options that we will likely be using: the 2D and the 2D axis symmetric. So this 2D axis symmetric is for the bent waveguide, and the 2D is for usual straight waveguides. And later they will ask you to select physics. And here you go to optics, wave optics, and the electromagnetic wave frequency domain, and to start set up your model. And in some cases that you don't see this, you have no optics or you're missing some part, you don't find the EWFD here, then that's most likely you have a problem with the license, that your license doesn't really have this model. Or alternatively, if you don't install this model, didn't install wave optics model is also missing. So yeah, just check that. And later when you are setting up the model, maybe some of you guys already worked with other some they call parametric CAD tools that you can actually do a parametric design that you first kind of define. You can first define your parameters in a separate kind of form, a separate sheet, and then okay, you use these parameters to construct your actual model's geometry. That's an important concept that actually helps a lot when you later want to kind of modify your geometry. So you don't need to go back, for example, okay, don't need to go back to the exact detailed feature, but then, okay, you can just change, for example, you want to make the waveguide a bit wider, you go to the waveguide X, okay, you change the waveguide X from 1.2 to 2.3, or whatever. Yeah, then just run the model again, you will be simulating for waveguide width of 2.3. Yeah, so you don't need to go to how we actually create the waveguides, creating this rectangle, you don't need to go there and change all the corresponding parameters. And another trick that when you are setting up the model is, okay, I would imagine most of the case that you are working with, with waveguides has a substrate of silicon or some other, maybe I don't know, some other 3-5 materials that have much higher index or whatever, I don't know. But okay, when you are setting up the model, you usually don't need to include a higher index handling substrate that you were using to back your waveguide. For example, if you are simulating, a silicon nitride waveguide on oxide on silicon, then you most of the case you exclude the silicon because okay. The best way to see this problem is probably you run the model with silicon once, and you will immediately realize that in this case, if you do it like that, COMSOL and also most other solvers will tend to find wave that is propagating in the silicon bulk instead of allowing your actual waveguide that you are interested in. So you usually just have to exclude that. That will simplify your problem by a lot. Yeah, and also later, if you go to my model, then okay, you will see that this is how I define my the simulation mesh. of course, COMSOL like almost other PDE solving softwares in computer. I mean, you need kind of discretization of the space. You are creating a mesh, and just to see a triviality here, only the inner box here that I meant is for the actual dielectric silicon nitride waveguide. The outer box is just defining a region that is to make the mesh finer within the box, so that you have a bit, I mean, a more accurate description of the fields that is closer, I mean, to where the field should exist. Yeah. Of course, you can do it. You don't have to do that, but may help a bit with accuracy. Yeah. And another a bit tricky thing is when you are setting up the model, you need to define materials and what materials you apply. You should use for whatever you have. So in our case, okay, our group traditionally kind of works with silicon nitride. Yeah, in silica substrate, and later now we have also some ferroelectrics involving like silicon niobate or lithium titanate. Okay, so first, but okay, the basics is really silicon oxide. You need to because most of the material, I mean, silica is ubiquitously used as a cladding for most of dielectric waveguides. Maybe only 3-5 people don't use that. Okay, even 3-5 people should also use that, but anyway, so but for this, we don't have, for silica, we don't have some in-house measurements. So we usually just use material from the library. So COMSOL has a material library. I think if you get to COMSOL, then you will see this icon that shows, okay, it has a material library. You can add material from this library, and it shows all different kinds of material. And the more accurate description for silica that we used for fabrication, for microfabrication, is probably this Malleuson's data for SiO2, silicon dioxide, and yeah, silica quartz, whatever. This Malleson, yeah, 1965. Yeah, you should find this one. And also just worth noting that if any of you have ever got a chance to use older version of COMSOL that is less than version 6, also be careful. There is a serious problem in that these versions that they have 2 Malleson data, and one of them is completely wrong. So yeah, you need to check the refracting index at 1550. And also as a rule of thumb, you should just kind of remember it. As you know, silica has also the lowest refractive index in the most common material. So it's just yeah, solid material, of course. Yeah. Water has 1.33, but you know that okay, it has a 1.43 refractive index around 1550. So you should also just as a sanity check look into that if you have a right refractive index. In particular, just because if you are using COMSOL version earlier than 6, just check that. Also for the waveguide core, if you are working with silicon nitride, then you can define you can for sure also find a silicon nitride in the material library, and for sure I think as we recall there is indeed an in-tray, but the problem is for silicon nitride, as it's common for some other dielectrics, it kind of varies a bit. Oh, sorry, I forgot to mention one thing. So for this dielectrics, you deposit or you kind of form by oxidizing silicon. Yeah, I mean silicon oxide you form in different way can have a slightly different refractive index. For example, if you are I don't know how familiar you guys with nano fabrication, but if you are depositing silicon oxide using PECVD, plasma enhanced chemical vapor deposition, then by tuning a bit of the gas ratio, by putting a more kind of precursors of yes, silane or whatever silicon carrying precursor, then you can kind of tune up the refractive index by quite a lot. So yeah, what I'm referring here to Malleson data is mostly accurate for kind of stoichiometric silicon oxide. but yeah, of course, you can have a bit non-stoichiometric silicon oxide. Usually, for silicon nitride, it's usually silicon rich, so that you have higher refracting index than this. Yeah, and kind of a reference is what you get by oxidizing silicon. You usually in nanofabrication we call it wet oxide or either dry oxide. These things are usually pretty close to stoichiometric silicon oxide. So the Madison data is mostly applicable. And if you have your customized silicon oxide, then of course you better measure it yourself by ellipsometry or some other ways. For silicon nitride, or the same problem also applies. If you have different silicon nitride get from different methods, you can also tune your parameter of your deposition a little bit. And you can have different silicon nitride. Silicon nitride can be either silicon rich or nitrogen rich. So refractive index can be higher than this or lower than this. This is what we are using for stoichiometric silicon nitride. Okay, the most stoichiometric as we can get using LPCVD and after high temperature annealing. This is what we had through our this is our in-house data. We send out for to a company called Volem for ellipsometry characterization of the refractive index. We got some parameters. Basically the refractive index versus wavelength curve. And then we do kind of this similar fitting to extract some parameters. Two different orders, and basically just fit it with such a formula, and you get all the parameters, and then we can put this into COMSOL, and you will just basically use the same model. That's the way for what we do for silicon nitride. And when you guys are working with probably different materials that you deposited yourself, the most accurate way is also just send your model. Send your material for our independent characterization for the refractive index, and then put this same fitted model into COMSOL. Of course, some of you may have capability to do this in-house. For lithium niobate or lithium tantalate or other anisotrophic material, the same principle kind of also applies, but things will be a bit more tricky because, of course, it's anisotrophic. So when you are defining your material, you need to be kind of careful. And there is a trick you can play when you are go to the in the material library. You right click, you get here edit. Then you have a dialog box that allows you to put not only anisotrophic refractive index, but something like a diagonal, kind of tensor-like refractive index. But also just your notes that refractive index itself is not a tensor. You cannot apply tensor mass directly to it, but only epsilon, only dielectric constant is a tensor. So you have to apply tensor mass to 1/n squared. So or just more practically, you can use a formula kindly provided by my colleagues saying, okay, you can the refractive index of the E wave or the O wave of a certain crystal that you are using, and this is how you define the XYZ components depends on the rotation angle of the crystal orientation. Okay, and later another problem when you are setting up the model is how you define the boundary condition. So for sure, for most of the cases we care about, the mode is confined within the waveguide core, and outside to the when the x or y it gets to infinity, the electric field should kind of decay to zero. Because of course we want a mode that is confined, that is around the finite amount of space. So you will need to kind of but in simulation, of course, you need to kind of enclose this simulation in a finite space. So there are different kind of options you can do. You can set up most simply put the kind of a metal case around your simulation region. Basically by defining what's outside as a perfect electric conductor or perfect magnetic conductor, PC or PMC. By basically assuming all the tangential field at the boundary to be zero. or you can use some other more advanced boundary conditions like impedance boundary condition or scatter boundary condition, or even using this so-called perfectly matched layer, which is also our mathematical kind of okay, you can understand it like a virtual material that is absorbing wave, that is incident at right angle to it. It's perfectly absorbing for light wave is incident for incident wave. To be honest, this selecting the best boundary condition is by itself a tricky question, and you can kind of refer to this application note or kind of example by COMSOL itself, the company itself. See how they simulate the leaky modes in microstructured optical fiber, and they are comparing the results you get from using scatter boundary condition or perfect match layer. These two can kind of sometimes give you most very accurate result, and they agree with each other. I mean, I would say all of these things kind of lacks a bit of mathematics rigidity, and when you are using this in practice, it's good that you do some convergence tests. I mean, most of the case we usually don't need to care about that, because I mean the further apart, the wave will decay to zero. But just to say which one converges faster, I don't know. You may have to try yourself. But in the model I sent you, you can either use scatter boundary condition, or use a perfectly matched layer, or disable all these two, and then you back to PEC, which is default for the they call it the physics interface. And once you have set up the model you want to simulate this problem for different wavelengths, then you can use either the built-in the built-in parameter sweep feature of COMSOL that you can you will just see here. I mean, in the reference model, in the solver configurations, you can also in the study you can set up a parameter sweep, and it's quite straightforward in case that you have parameterized your model. You have the variables that you can define in the table that I showed before, and then you can do sweeps automatically, and you can either save all the modes you have been solving for, or only save for some parameters is derived for you by using this called variable prop feature. And then this can reduce your file size for a lot if you don't need to save all the parameters. All the full field simulation. You only need to save, for example, effective index, and you don't need to save all this, but only calculate the value calculated by the prop. Only save that. You can of course do this with your custom script if you have some specific needs for doing the parameter sweep. So there is also a very useful feature. Once you open the model, you can also kind of save it as a MATLAB file. Basically, it converts every action you do when you create the model into a corresponding command in MATLAB. Maybe some of you prefer Python, but unfortunately that only works for MATLAB because of there is some kind of historical reason that COMSOL is built on Java, and MATLAB is also built on Java, so you can more naturally have an interface between these two. So, and once you have saved this model file as a MATLAB script, you can kind of do some customization. Of course, you can just put in your IP kind of to do whatever manipulation you want. And once you have a table of the effective index versus different wavelengths, either parameter sweep or whatever you do, then you can do this polymer fitting. That this is kind of except from the script, the Python script I also sent I think the files. So basically, you can once you computed the beta out of the effective index, then you can fit it as a do a polynomial fit of that as a function of of omega. Then you can extract the beta parameters, and also you can either directly compute the D2 and D3, the integrated dispersion by the expansion formula for the lowest orders, or you can solve for several resonance. Basically solving for the resonance condition to get the exact wavelengths that your microresonator have resonance, and then fit this wavelengths also again with a polynomial model against the indexes, the model indexes. Then you can also again in a different way get D1, D2, D3, maybe with a slightly better precision. Yeah. So I think that's all for for the description. If you have a question.
Yeah, I have a so some of the players are based on variable, and kind of just widely used concept with this kind of simulation.
So I think if you say numerical, then you say numerical mode solution, right? Yeah. Numerical also have a solver that can do exactly the same 2D mode solving, and I myself is using both. So one practical consideration is the numerical one is a bit more convenient because it somehow directly gives you the group velocity. Yeah, for some reason they can do either maybe a pertabulative calculation. Yeah, they can directly give you NG. It's a bit more convenient, but I experienced that it somehow has a bit less precision than COMSOL. Also, when when you are doing the meshing for the model solutions, you can only have kind of rectangular grids. So to kind of discretize your waveguide geometry, you will actually need much more grid points and to have a precise description. For example, if you are varying your waveguide height. Okay, for example, one problem that I'm doing actually just these days, I have a silicon nitride waveguide, for example, 5 micron wide and 200 nanometer thick. What I consider is if I vary the waveguide thickness by 5 nanometer, how much the effective index will change. For the most solutions, because it has only rectangular grid, because it's doing finite difference simulation, you have to correct to kind of discretize the vertical dimension to less than 5 nanometer to resolve this 5 nanometer difference. But for COMSOL, it doesn't have to, because all the mesh nodes are arbitrarily put directly on the waveguide geometry you have defined. So you don't need to discretize everything down to 5 nanometer precision. And so this kind of makes COMSOL converges, I think, much faster, in terms of precision and also memory requirement. Yeah.
Also, I was wondering, so you said you send your samples to external factories.
Yeah.
Is that because you don't have the capability?
Okay. So the thing is, if you go to the reference index model, we found out So first, maybe to explain a bit, if you are not so familiar with nanofabrication, so the state-of-the-art way of characterizing a refractive index of thin film is called ellipsometry. Basically, you are you have a white light source that's kind of with a certain polarization that is incident at an angle onto a thin film sample. And then you are collecting the refracted light with a polarizer, rotating polarizer and a spectrometer. And by kind of a kind of complicated fitting, you can extract the interference and the polarization resolved interference spectrum kind of, and then you can fit it with a refractive index model to extract the parameters of the refractive index. I think, okay. The reason that we don't do it is not because we don't have ellipsometers. We do have, and we also have all the in-house characterization. But it turns out that our ellipsometer only measures up to wavelengths of, I think, 1.8 micron. It have no capability to go to deeper infrared. And it turns out this fitting, and in particular, if you wanted it to be accurate of refractive index to be at telecom wavelengths 1.55, you will need to consider some data in the mid infrared. Otherwise, it's very difficult to get an accurate fit. And we also just have seen this in our in-house data, kind of have a slightly different slope compared to data we send for measurement at volume, which also is a maker of the ellipsometers. Because their detector can go up, I think, up to a few micron. They have mid-infrared detectors. This is a technical question, but
what precision do you get then?
it's very hard to just to quantify. But I would say probably 0.00 something. And if you guys are working with visible or shorter wavelengths, this will be likely much less a problem than if you have a ellipsometer that only measures up to probably 1.6, then that's probably enough. I guess if you guys are all set, then we can move to the exercises. Or you have more further questions? Yes.
We find effective mode area. With the load solution.
Yeah, for sure. I mean, this is what you can do in the post-processing. I mean, I think in the model I sent you, there is kind of something similar. That is basically once you have get the mode profile, you can not only plot it but also define integrals. Define arbitrary integrals. For mode area, how you write it mathematically is basically is your electric field is your intensity is intensity squared. Epsilon is intensity squared EA integral and square as a normalization factor and epsilon 4 EA. All right. I think 1 over that, but mostly just two integrals, and I mean you can define both in the post processing, and I mean I can later show you also in the exercise session how to do that. Any further question? Okay, then we can go to the exercise session. So these are something that you can try out yourself to maybe based on the sample model that I sent you guys. First, maybe to just try out how fine the meshes you need to have to get actually a reasonable dispersion parameter and also reasonable I mean, effective index. Also, yeah, maybe a bit more advanced. That's how you actually design your waveguide for micro resonator to get the, I mean, yeah, dispersion profile that you actually want. To get maybe a kind of dispersion wave when you are generating the Soliton. That's some specific wavelengths that you want it to be. Yeah, basically by doing this, you will need to have the right dispersion profile across a kind of a wide range of wavelengths. And yeah, you will need to know the beta 2 and beta 3. Yeah. I think also I shared also the files. So maybe yeah, you guys can already get started. I'll be happy to help with yeah, any questions. Now we are into processes. I guess we can stop recording.
Okay, I'll do.